Hi class. The plan for today is to continue on to section 3.4 titled Independence, Basis, and Dimension. These three notions are connected to vector spaces in general, but we will always try to first understand all of these things in the context of matrices, which is what we're truly interested in. And to motivate our discussion, I want us to revisit some problems that were assigned for homework and some similar ones that I had not assigned for homework. So these are from page 143 and maybe 144. Yes, 143, 144. Sorry for that pause. Hopefully you've had a chance to at least look at them, if not solve them. Okay, so problem 15 asks us to construct a matrix A which has the null space consisting of all linear combinations of these two vectors. So span is translation for the space of all linear combinations of whatever vectors are in the set that is under the span. So what does it mean for these two vectors to be in the null space of A? Let me start with the following. Let's focus on the first vector. What does it mean that 2, 2, 1, 0 is in the null space of A? Well, we can understand several things from here. First, A must have 4 columns. If you recall, the null space of A, by definition, was the set of all solutions X such that A times X is 0. So it solves this equation, A times X is 0. Well, what is A times X? It is a linear combination of the columns of A. What kind of linear combination? Well, the coefficients are all stored in X. So if this vector represents an X and it has 4 components, that means that A must have 4 columns. Furthermore, this equation over here translates into 2 times column 1 of A plus 2 times column 2 of A plus 1 times column 3 of A must be 0. Plus there is 0 times column 4, so I'm just not going to write it. So we know these two things just from the fact that this vector is in the null space of A. It means it tells us how to combine in a non-trivial way the columns of A. By non-trivial, I mean not all coefficients in here are zeros. So it says how to combine the columns of A to get a 0. So this says something. This says one combination. In other words, if I choose, say, column 1 and column 2, if I choose them arbitrarily, then column 3 would have to be set as minus 2 column 1 minus 2 columns 2, column 2, so that this equation would be satisfied. I cannot then choose column 3 arbitrarily. Now, what about this other vector? 3, 1, 0, 1 in null space of A. What does that tell us? Well, again, A must have 4 columns, so there is no contradiction there. If these two vectors were not with the same number of components, then definitely such an A does not exist. And then this number 2 with a star for the new vector says that, so this is another vector X that satisfies this equation AX equals 0. So it tells us how to combine the columns of A to get a 0. 3 times column 1 plus column 2 plus column 4. So it says 3 times column 1 plus column 2 plus column 4 equals 0. So now I have these two equations, which gives me quite a bit of freedom. One thing I don't know is how many rows could A possibly have? Well, I don't have any restriction on the rows just now. So could I even start with only one row? Let's give it a try. So the first equation over here says if I choose column 1 and column 2, then column 3 would be fixed. So if I only have one row for A, I could choose column 1 to be a 1 and column 2 to be a 1. Then I want 2 plus column 3 to be 0, so then column 3 would have to be negative 2. Column 4, there is nothing about column 4 in this equation, so I'm not going to do anything because I know that they have another equation that involves column 4 that must also be satisfied. So column 1 and column 2 have been set up. What about column 4? So 3 times column 1, that's 1, plus column 2, that's a 1. So that's 4 from the first two columns. Plus the last column should be 0. Well, that means the last column better be a negative 4. Could this one row, like this, be our matrix A? The answer is no. Why is that? Because I can see one more vector in the null space of A, which is linearly independent of these two vectors. But if another vector in the null space is linearly independent of these two, that means that it would not be in the span, because being in the span means that whatever vector I find in the null space would be a combination of these two vectors. So what other vector am I seeing that is in the null space? Well, you see column 1 and column 2 are the same if this is all I have. So they're dependent. In fact, if I only have one row, what I have is a single pivot. So if I have only one pivot, that means I have 3 free columns. That means I have 3 vectors which go into the null space. But my null space is a span of only 2 linearly independent vectors, not 3 linearly independent vectors. So what I see is that I have to have at least 2 rows. Well, that's easy enough to fix. So I like the first row that I have here, no problem. Let's just add another row. So perhaps I could put a 0 here and a 1 there. And the reason I do that is because I want the first and the second column to truly be linearly independent. Now, I need to make sure that the two equations, the one over here and the one over here, are satisfied. So from the first equation, for the second row, I have 2 times 0 plus 2 times 1, that's a 2, plus column 3 should be 0. Well, 2 minus 2 would be 0. So, I see I have a mistake in the first row. So that should actually be a negative 4. I don't know why I wrote negative 2. But the one in the second row should be a negative 2. And then from over here, column 1 is a 0, so we don't have to look at it. We have column 2 plus column 4 needs to be 0. So since column 2 is a 1, column 4 better be a negative 1. And now if you look at this matrix, you see that it has 2 pivots. You see that the first and the second columns are pivot columns, therefore they're independent, whereas the remaining 2 columns, they're free columns, they're dependent on the first 2, and in fact, the linear combinations or 2 linear combinations that give us zeros are these 2. So yes, this is the null space. This is a matrix A. Could you add another row? Absolutely. The only condition is that you have to have 2 columns which are pivot columns and 2 columns which are free columns. That is the only way to guarantee that the null space of A will be precisely span of these two columns. Now let's look at another example. Now we have another matrix, an A, so that the null space contains only one vector. Well, is a linear combination of only one vector, meaning that every combination of the columns of A must be a multiple of this vector. So it's interesting. Here we know that the null space of A is just a line, whereas in the previous case, we in fact had a plane. Now we have this sense that a plane is bigger than a line. It obviously is, although if we were to try to count the number of elements, well, they both have infinitely many elements. What I'm hinting to here is the notion of dimension. Intuitively, we understand that the plane is two-dimensional, whereas a line is one-dimensional. I will make this precise, what is a dimension and how it connects with a basis for a vector space, but this is just to point out to it. So if I want the null space of A to be exactly this one vector, what do I know? Well, what I know is that A must have 4 columns. So A, again, must have 4 columns. Now, if A has only one row, that would mean that A has one pivot. Or rather, let me put it differently. Having only one vector or having only a line that describes the null space. So knowing that all elements, all vectors in the null space are multiples of a single vector, that tells us that A must have one free column and 3 pivot columns. Otherwise, we would have more free columns, right? We have to have only one free column and A must have 4 columns. Therefore, A must have 3 pivot columns. So we know that A must have 3 pivot columns and therefore one free column. How can we get 3 pivot columns? This is very important. How to get 3 pivot columns? Well, you have to have at least 3 rows. So these 3 pivot columns imply that A must have at least 3 rows. It could have more, but it has to have at least 3 rows. So we're trying to construct the easiest example possible, at least I am. So I'm going to start with the first 3 columns. I'll take them from the identity matrix and I'll stick with 3 rows because why not? So I'll do 1, 0, 0, 0, 1, 0, 0, 0, 1. So I can always choose the first 3 columns to be the pivot columns because that's normally, it's not, they don't have to be. This is not the only way to combine these columns, but it's just one way. And what do we know? How can we figure out the last column? Well, the linear combination, so this vector, it tells us that 4 times column 1 plus 3 times column 2 plus 2 times column 3 plus column 4 must be 0. So now if I substitute here and just start adding up, I have 4, 0, 0 plus 0, 3, 0 plus 0, 0, 2 plus column 4 plus something here must be 0, 0, 0. Well, this sum is very easy. This is just 4, 3, 2. So I see that this other vector better be -4, -3, -2. So I know that the last column must be -4, -3, -2. And this A will absolutely satisfy the null space in question. So we'll have this null space. In fact, to confirm, you can just give that a try.